So welcome back. We are still on chapter 3. This is part 3 of that chapter. And the last section of chapter 3 goes into some basics of acid-base chemistry, which from what I understand for those of you guys in AP Chem, this is something you guys are going to spend a decent chunk of time looking at this year. So when we have water molecules in their liquid form, they're constantly disassociating and reassociating in solution. And that's all due to those hydrogen bonds. So here I'm taking a look at two water molecules. They're hydrogen bonding to each other. And what happens is that hydrogen bond every now and again will become strong enough just to kind of rip one of those hydrogens off and attach it to another water molecule. What we create is a hydronium ion. So there's an extra hydrogen and a nucleus, an extra plus. That other water molecule then that lost its hydrogen hangs on to hydrogen's electrons and becomes this hydroxide ion, which is a minus. Okay, so plus and minus. Now this is a solution or chemical reaction that's happening in equilibrium, hence the reversible arrows here. And so in pure water, we get this sort of state of dynamic equilibrium between the water molecules themselves and then the dissociation into those hydroniums, or what we frequently will refer to as an H+, just to simplify things, and a hydroxide ion. Okay, so this is going back and forth at the same rate in pure water, and so we don't really see any actual pH change. So what happens then when I add more H's, more hydrogen ions, or more hydroxides? So your acids are, by definition, a substance that's going to increase the H+ concentration. What happens when we take an acid, dissolve it in water, it's going to disassociate, and as a result, add additional H+ to the solution above and beyond what water is already sort of doing in this dynamic equilibrium. So something like hydrochloric acid disassociates into HCl, or is HCl, disassociates into H+ and Cl-. So we're going to increase the number of H+ already that water's creating by adding more of them to that, by adding something like HCl, some sort of acidic compound. Your bases are going to be solutions that reduce that H+ concentration. Now they can do that in two different ways. We can talk about something like ammonia, which is NH3, and ammonia has an affinity to actually accept an extra H+ and be an ammonium ion. It's actually a little more stable this way, and so it's going to take out extra H+ from solution, leaving a higher concentration of OH- because now this H+ is connected to this and can't go back and connect to that hydroxide ion that H+ originally came from to reform water. Or we can reduce the H+ concentration indirectly, where I have something like sodium hydroxide, the NaOH, that's actually going to disassociate in water, leaving me with a sodium ion and a hydroxide. That hydroxide ion is now free to combine with H+ to form more water. Okay, so either way works as a base. So how do we utilize this? What is this important for? Well, it's your effects of pH. So your solutions that have a higher H+ concentration are your acids. All right, remember that on a pH scale, they're going to be less than 7. Your solutions that have a higher OH- concentration, which O, by the way, means they have a smaller H+ concentration, right? This is all works in conjunction with each other. Higher OH- or lower H+ is your base. They're going to have a greater than 7 pH value. And when you get solutions that have the H+ and the OH- disassociating in equilibrium, those are your things that are neutral, all right, and have a value of 7. For most biological fluids, your pH is going to be somewhere in the range of 6 to 8. That's typically what we're looking for as something that's going to be functional in most organisms. Just another quick reminder, we can have strong acids versus weak acids, strong bases versus weak bases. So if we talk about something that's a strong acid, it is something that completely disassociates when it mixes with water. So you're going to end up on either end of the extreme on your pH scale. All right, either very high H plus concentrations or very low H plus concentrations, which means you have a very high OH minus. Your weak acids and bases are going to be the ones that are going to keep you closer to the range of what most biological systems are used to and require because they don't completely disassociate. All right, and so that reaction is going to be reversible. Just like water, it's going to be able to disassociate and reassociate. And so as a result, you don't have a pH on either end of the extreme. You're now kind of towards the middle of the pH scale without actually being at 7. So, pH scale is just this measure of hydrogen concentration. Okay, although when we looked at back here, I said it could be, they kind of coincide with each other. Your pH scale really is based strictly on your H plus concentration, but you can infer your OH minus as being the opposite. Okay, and your pH scale is going to range in value from 0 to 14. 0 being the most acidic, 14 being the most basic. If you take an aqueous solution at 25 degrees Celsius, the product of your H plus and your OH minus constants can be written as concentrations. That's what the brackets mean. Okay, so your concentration of H plus, your concentration of OH minus should give you 10 to the negative 14. All right, what does that translate into? On your pH scale, it's a value of 7. Okay, so when your H plus equals your OH minus concentration, you're neutral. If your H plus is greater than your OH minus, you're becoming more acidic. All right, when your H plus is less than OH minus, you're becoming more basic. Now, your whole pH scale is based on log. Okay, it's a logarithmic scale. What does that mean? It means every time you're moving a unit on the pH scale, so from 4 to 5 or 7 to 8, each of those units actually represents a tenfold difference in those concentrations. So if I'm going from 7 to 6, I'm increasing my hydrogen concentration 10 times. I'm decreasing my OH minus by 10 times from 7 to 6. Okay, so that's what that's getting at. Last thing that's incredibly important for living systems are these buffers. Okay? All the chemical reactions that are going on in living organisms constantly are going to be creating products or using substances that are going to change the pH of its environment. That's a big problem when living organisms have such a small range of 6 to 8, and depending on the organism and the system you're talking about, sometimes it's even tighter of a range than that in terms of what they need to survive, pH-wise. So there are tons of buffer systems out there in nature, and all a buffer is a substance that's going to consist an acid-base pair, and it's typically a weak acid with a weak base. And they work to minimize the changes in pH when you get extra acid or extra base added to that solution. Okay, so they're either going to work by accepting extra H pluses when they become in excess in solution, so we're getting too acidic, they're going to bring it back, all right, or by donating H pluses when the solution gets depleted, so when we're getting too basic, it's going to add extra H pluses to help bring that back. Classic example of a buffer system in the human body is the carbonic acid that's in our blood. Okay, these get produced by our respiratory functions, cellular respiration, okay, and so we have this system in our blood that when we get too acidic, it's going to give off extra H pluses. All right, when we get to basic, it's going to add the H plus back to solution so that we can keep your blood pH, your body pH, at a relatively consistent level. When this system goes awry, that's when we get all sorts of issues, and we typically see it as somebody breathing. All right, they're either trying to expel extra CO2 from their blood because they're getting too much of a pH swing, all right, or their breathing becomes very shallow because they're trying to go the opposite direction. And so when we get to cell transport, and we'll talk a little bit about your respiratory system, your cardiovascular system, and so this buffer construct for this particular example is going to show back up.